Good afternoon, all. Today we have with us our electronics and communication pass out alumnus, Mr. Pranav Parikh, and he has been working with eInfochip Limited, situated at Ahmedabad, and this company is renowned in the field of Vlsi. Mr. Pranav Parikh has completed his graduation in 2015, and he's a student of 2011 class. Pranav Parikh worked closely with designing team at eInfochip, and he has extensive expertise in debugging large and complex code for error and rectification for the bug removal. Pranav is also expert in developing script for automation and function related to regression analysis. Along with this, he is also expert in handling tools such as Cadence, Xrun, SimVision, IMC, Synopsys, VCS, and other. Moreover, he is also expert in different methodologies and languages such as System Verilog and UVM. So Pranav has a very strong profile in the field of VLSI. So now, without wasting much time, I would welcome Pranav on behalf of EC Department and Parul University, and I hand over this session to Pranav Parikh. Welcome, Pranav Parikh, once again on behalf of EC Department and Parul University. Thank you, Pranav.
Yeah, thanks a lot, Umang sir. Yeah, it's always been a pleasure getting connected with you guys, and it was a wonderful time when we were part of this career journey with Parul University. So, as Umang sir rightly pointed, currently I'm working in eInfochips, which is company basically you would be aware, which has a main role of service providing, and they work for both the domains like embedded as well as the ASIC. So their entire service provided for the they have different domains, and they provide all kinds of services to the different kind of clients. So when we start, so for the students, I would like to say, first of all, hi to everyone. And yeah, so now you all might, I'm not pretty sure like you are in the last sem or what, but yeah, so you would be starting your journey within some time in the actual industry part, and you will gain a lot of experience along with the things we have studied till now. So it would be an amazing journey as and when you will start in the actual industry, and you can correlate the things you are doing currently in the college for your whatever academic part you are studying and the interest which you develop. So in reference to that, you should always think your field of interest, and then you should select your stream accordingly. So today I'm going to present a topic for the career opportunities in the field of VLSI. So you all might be aware that in our electronics and communication, there is a subject for VLSI. So, and VLSI stands for Very Large Scale Industry. So in this, you might be aware that there are different subdomains inside of VLSI. It is a huge domain, as we say. So there are many opportunities and many subdomains inside this particular, you can say, superset of VLSI. So based on the interest and your liking, you can always think, or you can get into this field. So what I would suggest is, first of all, definitely, as we have been learning since we are small, we should begin our career and we should pursue the things which we are interested in rather than just doing it for the sake of doing or getting into the field wherever everyone is going. So I would suggest to follow your dreams and your interests, and then you should think of a particular domain you want to enter in. So like for me, if I would tell you, like whenever we were studying this subjects in our academic time, so we always thought of like getting interested in the small things like the resistor, transistor, or whatever the components are there inside our electronics. We are always attached with that small components as well. So we always can relate our feelings with this particular domain where all this part will come together and how actually a chip is formed. So this was our interest being developed during the academics parts only. Like we want to join this or we want to get more knowledge in this. So that was the way. Like whenever we did the practicals as well in the academics, it was very interesting to see how the PCB is formed, how different components are connected, and how the circuits are formed, how exactly it works in the real world. We everyone are surrounded with the gadgets and the uh, new technologies surrounded by us. So we all know that engineers are like reason or the hand behind this, where we find these new technologies and we help people around us to get their life simpler. So this VLSI is again you can say huge contributor towards this new technology and the new easiness that is being provided to the person's life in the day-to-day life. We see that we are surrounded with day in and day out, we are surrounded with the small gadgets or the electronic things which has some electronic equipment inside it. So starting from mobile, we are all using our mobiles in the day-to-day life. Then there are n number of gadgets which we are using in our daily life: TV, fridge, whatever, washing machine, XYZ. So not only us, even the elder ones and the smaller ones, all of us would be some way connected to the electronic gadgets. So even in the medical field and all other fields also, you will see that there are equipments or the gadgets which has electronic devices with inserted within them. So you will always be curious to know that how exactly this all gadgets or the equipments which you are using actually are being prepared, and how exactly they are prepared in the back end. It is always a user interface that is visible to us, and we like or love using the gadgets which we have. But there is a huge process, or you can say lakhs or more number of peoples or engineers working behind the thought process itself, and then bringing it to the actual world in the form of hardware. There is a lot of effort as well as uh, thinking and you can say research and everything is invested behind each of this part, so that we can get a best equipment in form of a hardware, and it makes our life easier. So even you will be using the laptop daily. Now in the times of corona, you are learning things online, and the classes are even at the home place only. So again, that is an excellent example where how these small mini computers, or we can say the laptops, have reduced in size when we think from the time when it was actually being invented. So you all must be aware, we have heard the stories and even seen in and even read in many books that there were the computers which are in the size of a room, entire room, and from there we have came till this now, even mobile, tablet, or small devices, the mini laptops and everything. So now it is said that the actual computer is the size of this small fingertip. So this and small chip would the size of the chip would be this much small, which would be functioning for the entire computer. So this is the power of our electronics and the power of VLSI, which has helped to you can say shrink the size of a hardware, as well as best performance. I won't say better, but best performance from the time which was before to till the point now we have. So the speed, you must be hearing the terms of the speed of the like the RAM and the ROM and all the different processing systems which are involved inside the lab, our laptop or the computer. So these all things have evolved with time, and with the better research and better work, it has came till a point where now it is way beyond our imagination, where we have thought that this was actually possible or not before 15, 20 or 25 years maybe. So at that time, no one thought that this kind of technology would be there, and we can reach the world this much easily with these small devices across our hands and across the people. So now we all are connected. In this tough time, you all are aware that we are connected with this with the help of these gadgets or the equipments. How closer we are, even though we are not at the same place, it feels like we are close to each other, and we can share each and everything between us. So that's the beauty of this electronics field, I would say, and in particularly the VLSI stream, where this helps to build these kinds of gadgets and equipments which would actually help each and every individual in their day-to-day life. So now I would like to give some overview in specific to this ASIC division. So as you are all aware, I'll also give my brief introduction to you guys. So currently, I am working with eInfochips since 5 years, and I'm working as a senior verification engineer at eInfochips. And my job profile is as the name suggests, verification engineer. So basically, I validate the back. This is all the thing which is done before a chip is actually being manufactured, or we can say a hardware is actually being prepared. So before this hardware is prepared, there is a long cycle of this design and verification which is undergone, and I am part of one such subdomain inside that. So I'll explain you how exactly this ASIC works, and how exactly the born of this chip is happened. So let me walk through this process for all of you, so you get some idea that how exactly this hardware of a small chip comes into existence in your day-to-day life. So as a layman or as a common person, you would never come to know that what all things are there behind your electronic gadget or the equipment. You might, as an engineer, you would be experiencing that if someone has a particular interest in that field, then you might have opened your gadgets at home or at any place. You have seen that what exactly things are there inside a gadget or equipment. But as a normal person, no one knows that what all things are present inside the hardware or the equipment which you are using. So this is the journey, or this is the process which leads to this hardware development and chip designing. So it is, I would say, the most beautiful thing to experience and learn that how exactly small components like a resistor, transistor, MOS, CMOS, and MOS, all things which you are studying currently, you might be studying currently. So that is used and converted into an entire chip, and then that chip is used inside this big equipment or a gadget, which makes our life so easy. So yeah, I will walk through the below mentioned points today to help you understand how exactly this ASIC works, how exactly this ASIC industry is, and what are the subdomains and the opportunity inside the ASIC industry. So first of all, I'll brief you a bit more on the ASIC part. What is ASIC and how exactly it works. So there is a slide for an ASIC design flow. What is the entire flow for the ASIC? Then there is sub bullets for the specification, Rtl coding. So I'll explain you bit in detail for each of these bullets, where you will get an brief understanding on how exactly these fields are and what are the opportunities again in these subfields if anyone wants to target a particular area of interest from their point of view. So yeah, there is points for specification, Rtl coding, test bench simulation, synthesis, placement, and route. Then there is sign off, and the last thing is tape out. So word tape out itself indicates that something is tapped out in the real world. So that is actually the real chip when the hardware is being prepared and coming into the actual world. So that is the thing which is prepared in the foundry or labs, you can say. So yeah, I'll walk through that how exactly that also works. But for now, you can think of a point where there is just these small gates and transistors and small are electronic equipments which are actually formed together, designed together, and placed on a actual die where it will become a chip, and it has some IOs. As you all know, that every chip has some IOs, input and outputs, and then it is used in some particular as per the requirement. It is used in a particular gadget or equipment. So yeah, the first slide here you can see I have put is what is ASIC. So from the picture you can see and you can relate that this is kind of raw chip which it looks like. So this has lakhs, you can say millions and trillions of gates and electronic equipments bounded inside it, and together it forms a beautiful structure which actually we can call it as a chip, and that can be used in our actual world for different requirements. So when you will see the process that how exactly that those gates and CMOS and MOS are getting connected, and it is forming some specific, it is fulfilling a specific requirement. So that is a, you can say, area of interest what I was talking about, that if you have the keenness to know that how exactly these things are prepared and how it is converted for a, the things are gathered and placed on a particular die and converted into a chip. So this is what all ASIC is about. So the name ASIC stands for is application specific integrated circuit. So again, the name itself suggests that it is application specific based on the application. This particular chip or the gadget, based on the gadget, this particular chip is designed, and then it is used as per the requirement in a particular place. So that is what an ASIC is. So a raw chip, any raw chip, we can consider it as an ASIC. The processor, controllers, everything has a chip designed, and we can place it and use it in for a particular application based on our requirement. So again, the next point is like build by connecting existing circuits blocks in new ways. So this is kind of generic. Now once this chip is manufactured and coming in as an hardware, so now you can use it in many different applications or various equipments where similar kind of requirement is there. So this single chip is used for, you can say, n number of applications in the market. Wherever the requirement is suited, this particular chip can be used inside that structure, and we can get that functionality of the particular requirement. So again, the challenges, I would say, and the things or the technology which we are working upon are the being it a high speed. So now with next generations coming in, you are learning and hearing about the speeds being a major factor, the 3G, 4G, 5G, even the internet speeds you can correlate. So always fast world is, it is a never ending thing, and it is always beyond our imagination that what would be the final point where it will actually be halted. But there is actually no limit to this. The sky is the limit, we can say. So it is kind of high speed structure we are working for the betterment for. Then the lesser area, again, as the name suggests, lesser area means the chip size and the die size are getting smaller and smaller, and this all transistors and gates are fitted on the small layers of the die. So this will make the actual component of the equipment so small and handy, so that we can carry with us normally in the routine life, and it is easier for us to work or make our life easier. So lesser area is again a very important, you can say, challenge, which for which we are doing a lot of research work, and again the implementation work. So then there is point of power consumption. So you now if I would like to give you an example for correlation, then it would be kind of let's say your mobile device. You are using this mobile device in a day-to-day life, right? So whenever you are using different brands and different kind of mobiles, you would be comparing some common things, like whenever I play a particular game in this mobile, then it is getting heating very easily, or whenever I put it in charging, it is getting heated at a very high temperature. So this kind of things are the actual, it has a background process where the functioning of chip plays and the placement and routing and the formation of chip, design of chip plays a very important role. So the power consumption is decided at the initial time, where based on its usage and the components used and the technology used, the power consumption would be decided that this for this particular kind of application, it will consume this much of power and it would generate this kind of heat, or it will work under this circumstances or this much temperature. So there are various points which are considered for this power consumption. And then there is one biggest point in this ASIC industry is time to market. So in this growing world of competition, you all know that for a single kind of application, there are multiple vendors across the world, and many countries are working on the same thing, which they would like to bring in the market as a first customer, for the being a first vendor, so that it would be something different for the customers and the consumers like us, who will be attracted for the new technology and will buy that thing, and it will be actually beneficial and advantageous for them in terms of sales. So time to market actually means that the time actually taken for the idea or the architecture to be converted into actual chip or the hardware. Sorry. So whenever this idea or any representation we have thought of for particular application, we bring it into the in the form of hardware, and then actually it is being integrated in the application based SoC chip. So that would decide like how good that product will be, or how more its sales would be. So in this competitive world, it is very important factor. We can say that time to market should be as less as possible, but at the same time, the quality is not at all compromised. Like the brand name should not affect, because ultimately once the brand name is spoiled, it is a loss of millions and trillions rupees for them. And even beyond rupees, it is the brand name that is being degraded. So that is not acceptable for them, being a big vendors. So for chip, if I say, you can relate the vendors, like there are Qualcomm, ARM, Broadcom. So there are wide range of vendors you can think of who are providing services for this processor or any kind of. There are multiple kind of, again, ranges, and based on the applications, varieties of the processor and the chips they are manufacturing and providing to the different customers for different kind of applications. So this time to market, yeah, it is a point like very important point for them to take a note of. Then yeah, in this slide, this is what actual ASIC design flow looks like. So you guys can understand this properly and try to relate yourself, like what is your interest and what particular thing you would like to do, and you are getting attracted towards from your interest. So there are for our engineering part, there are again you can say divisions or sub part for the entire process where you can work in. So in this, each of the divisions, there are engineers required for doing a particular functionality, and based on your interest, you can try to get into that particular domain. So now in this flow, you will get some idea that how exactly from scratch an idea is being converted to actual chip, and what are the steps behind that. So starting from point number 1, here you can see there is a chip specification. So first of all, it is the raw idea or requirement, you can say. Every problem has a particular solution. This is a common saying, right? So based on the problems in our day-to-day life, we analyze that if for this particular problem this kind of solution would be there, then it would be much helpful or much easier for us. So this is a kind of simple statement, problem statement, which will lead to some innovation or some discovering or inventions. So observing this in our day-to-day life, the problems which are facing leads to the, you can say, discovering the new ideas and technologies or the requirements. So first thing would be the chip specification. Once this problem is identified, then there would be a constant backend team looking for a solution for that, and they would come up with a specification that we have this kind of thought process and we want to convert it into actual implementation, and a chip should be manufactured so that it has this particular functionality and it can be helpful in this particular domain or application. So there is a team which works on the specification part, that what exactly the requirement is. They gather the requirements and then they create some proposals and plans that how and what all technology or what all. So it has a, again, wide, you can say, deep knowledge required for this particular domain, where they have more of an expert kind of thing, persons who are working on this, where they know about various technologies and you can say combinations which can be useful, like the advantage as well as the disadvantage of using a particular technology. So even you all might be knowing that our technology has many advantages, but at the same time there are some flaws as well inside that. So we need to select a proper proportion of what thing we want and what things we can consider as a low priority, or we can side of that thing. So based on this requirement, a particular specification is prepared. Now once the specification is in, then there is a team of design entry and the functional verification. So particularly, as I gave my introduction at the start, I am working at the point number 2, where it is a functional verification. So at point 2, there are two teams actually working in parallel. The design entry is basically in our terms, it is called RTL. So register transistor logic is the full form of RTL. So our registers, the gates or the technology which you are currently understanding or learning in your academics. So that are the, you can say, base points of this part, where for that actually there are particular languages. The HDL languages you might be aware about in the VLSI domain or the subjects you are learning. So the HDL language, like Verilog, system Verilog, are the different languages where those are particularly used for this design coding and design entry. So there are engineers particular to this domain who write a particular code in the design. So they, after writing that code, that actual design would be prepared, or the RTL would be prepared, you can say. So the VHDL language is again the thing you will be learning currently in your academics. So using that kind of languages, they prepared a actual design structure, and then simultaneously you can see an option of functional verification, where our role comes into picture, where we write a test bench, or you can say a stimulus in common terms, where if I can relate you for anything, like you are understanding a thing of NOT gate, right? Like what a NOT gate, if I provide an input 1 to the gate, then it will give an output 0 at the other end, right? So this is a kind of stimulus, that 1 is the input, the stimulus is given as 1, and I know the functionality now that I should expect 0 at the other end. So whenever this 1 is driven at the input of the gate, I will expect that output is 0. This is kind of simplest relativity I can provide, like based on the expectation, we are given the specification. So we know that what should be the expectation at the output side. So based on the input we have given, we have checkers written inside our test bench. The entire structure around the design which we are coding for this verification is called test bench. So inside that test bench, there are multiple components or the test cases or the stimulus, you can say, different kind of stimulus which we are providing to the input of the design. And then based on the specification, we are expecting that this kind of output should be there at the output side. So based on this entire process, a test bench is written in, again, it has a specification, language which is system verilog, and the methodology which is UVM, that is most commonly used across industry. So with these different kind of languages, the design and the verification domain is working on. So C, you also can relate it with C, whosoever has an interest in C or C++. So those are the basic languages, you can say, which you can so if you have interest in coding part, I would say you would relate a bit to coding, then you can definitely think of this stream which is called design or the functional verification. So you can do a designing from the specification you have, and on the other hand, you can do the verification as well. So the verification engineer has a great role, as well as I would say it has great stacks in terms of role they are doing, because if they miss out on anything, or they miss out on any bug or feature validation, then once the hardware is prepared, we can't do anything about it, and it is actually the loss for the vendors in terms of billions and trillions of rupees. So it is very you can say precious or important job we should be proud of, as well as do it with that much accuracy and responsibility, so that at the end we don't miss out on anything, and there is no flaws coming out at the later stage when the hardware is being prepared. Because once the hardware is again thing which is getting manufactured in multiples of number, like it is not one or two chips that would be manufactured or produced in the foundry or the lab. It would be again millions and trillions of chips would be coming out at the same time for a particular design. So once that is it has a great cost for the entire process of this, getting a chip coming out from the foundry. So it has again a separate process and its own you can say stake in terms of investment done after that part. So it is, as I mentioned, a great responsibility for us that we perform this job properly, and make sure that whatever specification or whatever intention of the requirement is, we fulfill that and validate it again at the same time with utmost accuracy, so that after it is being converted into hardware, there is no bug left and no flaws observed at the end. So yeah, that is point number 2 in brief, where you can think of design engineer as well as the functional engineer. Then point number 3 is RTL synthesis. So once this coding is done in a particular language, the VHDL language you can relate with, that is Verilog hardware descriptive language, or the again very simple Verilog language. So there are different kind of languages in which this RTL designing is done. The design code is written. Now it has to be mapped to a proper industry standard and tools which are used inside the engineering department. So this RTL synthesis would actually convert that raw design code into the synthesizable code, and whatever industry standards or whatever particular standards are set, based on that it will try to synthesize the entire design and convert it into a netlist, where all that entire netlist can be then directly used for the manufacturing purpose, like in the foundry for the next level of process, that is creating the chip from the die. So the third point here mentioned is the RTL synthesis. Then so again I would like to highlight one point is the point number 1 and 2 would be considered as a front-end engineering department, where it would be done at the initial level and then at the front side of the flow. Sorry. While from starting from point 3 until point, I will say 9 or 10, it is a more of back-end process where with the use of different tools and our human brains, we try to I will explain the different points here, but we will try to bring in a hardware which is very compact, very powerful in terms of area, then power transmission. So there are different parameters which should be looked upon, and so for each of that there are some processes to be followed, and again for that each process and the domain, there are some engineers associated with that who do this wonderful job of designing the chip. So yeah, point number 4, you can see that it is a partitioning of chip. So now once this RTL synthesis is done, so it will be a kind of form of gate logic and the flops and the structures which we are using in our actual electronic industry. So now this different equipments, or you can say components, needs to be actually we need to convert it in on the chip level. We need to form a hardware. So for that, a design, we need to do design steps like how and where exactly you are doing a PCB designing, right? You might be aware of a flow for PCB designing. So at that time also you would be doing some layout structure, that what all components you would be putting at which place, what would be the connections, how you would be routing the wires and doing the connections. So that is kind of small structure or small, you can say, project on which you are thinking and working it with, but you can definitely relate it with the actual chip designing, where the small gates and the transistors and this flops and everything are getting connected, synthesized and connecting on the actual wafer space or the die, we can say, and then actual this hardware chip is being prepared. So that is point number 4. Then point number 5 is design for test insertion. So in short form, we called it as a DFT. There was a field for design entry, then there was a field for functional verification. This is one more field of DFT, and they have their role in terms of they are responsible in terms when once this hardware is being prepared. So after that, you also might be relating with FPGA part, right? You might have seen a FPGA board where actual based on your application, that FPGA board would be doing some particular application, performing some particular set of activity. So once this, after point number 11, the hardware is being prepared. So even though we have done some verification and some testing before the hardware is being prepared, but even after this, there are possibility. It is very less, but still there are some possibilities that the hardware does not work as per expectation, and there are some you can say impurities which might be getting affecting the actual hardware, and it won't be allowing the application or the chip to be working as per the expectation. So it needs to be tested at that point, and then for testing after this hardware is being prepared, this DFT field is important, where they insert some test vectors at the time of chip fabrication, and after the chip is being coming in as an hardware in our hands, we can use this testing points in between to check that proper input is being coming out to the output as per the expectation. So if I give an example, then let's say you are aware of flip-flops, right? So now the flop, let's say D flip-flop. So if you are giving some input to the D flip-flop, and at the with synchronization with clock, you would expect that the output would be coming, the Q and the Q bar things, the truth table would be already aware of, right, for the flip flop, D flip flop. So based on this, based on some input and the clock, you would be expecting some output would be coming out. So in this case, let's say after the actual hardware is being prepared and the manufacturing is done, so it might be the case that it is not working as per the expectation. And if, as I mentioned, if I'm driving one to it and I'm expecting that after some time one should be coming out at the Q or the Q bar signals as an output. But let's say there is some issue with the hardware and it is getting stuck at the particular values, or the connectivity is not proper. So this is a very basic kind of issues which I am pointing to. But that way you can relate things like how and where the role of this particular field comes into picture. So if I'm driving one to that input and the output, we are expecting that after particular clock cycles it should be coming out as 1, but due to some issue it is not coming out as 1 and it is getting stuck to 0 at the what is the initial value, which is the initial value of the chip. So this is an issue, right? So how would you catch that at the later stage once the manufacturing of the chip is done and it is actual hardware which is there with you? So it is not simply that at the input of the pin you are giving this some voltage or some data and you are expecting, like in normal terms, I'm relating to you that you would be connecting an input IO of the chip to some value and giving it some voltage, and then expecting that some value should be coming out at the chip output, right? This is how you would be testing your application or the PCB project which you would be doing. So in that case, for the internal to the chip, there are so many huge logic inside that particular small chip. So if you want to test that part and if you want to check that where exactly it is getting stuck or it is not working, in that case this DFT field, you can say that it would come into picture, and the test vectors or the stimulus which they have inserted at the time of before the time of being manufactured, it would help, and it can help to debug in that case. So yeah, this is again a subfield in this ASIC flow where engineers are working for different kind of test vectors they are inserting inside the chip, and which can be used later for the validation or the testing part. Yeah, then next point number 6 is the floor planning. So floor planning, as the name itself suggests, and I have also mentioned it just before some time, that for your PCB you are thinking, right, like I will put this chip at this point, then I will connect with the wire to this particular sensor, or then I will connect it with some motor. So this is kind of a raw project you would be thinking on a PCB, or you might have worked on. So this is a small floor you can relate it with the floor planning that you are doing. But in actual terms, for the chip, when the floor planning is a process, it again is very important point, you can say a key point at the ASIC flow, where if the floor planning is not done properly, then it might lead to incorrect connections at the end, or maybe noise getting generated, that power analysis, the power consumption would be very high. So the later points of the flow would automatically get affected by this. So floor planning is an important or the key step you can think of, where with the help of tools, engineers place and route these gates and logic inside our actual chip to how exactly and where it is going to be placed, and what kind of between two nodes, what would be the time actually it would be taking to travel. If I'm driving a one at particular input, then reaching it to point B, again I'm expecting one at point B, but what amount of time it would take, how many number of clock cycles it would take, so all those calculations would be done, and connections are actually being finalized at this point where floor planning is done. So that is point number 6. Then 7 is again the placement stage, where placement, routing, you can relate like the wired connections which are done, and the data that would be traversing inside the chip. So from which block to which block the data would be traversing, and how exactly, like what kind of data we are expecting, and how much power would be utilized inside, like from reaching from this point to this point. So what amount of power would be required, what would be the speed of the clock, and at that speed how the what would be the power that would be consumed. So all those stuff would be decided in this particular stage. Then there is a clock tree. Point number eight is the clock tree synthesis. So as you all are aware that all of this would the entire ASIC is like the first point would be the clock. So once the clock is enabled, then only some functionality or some input. You can consider clock as in with reference to input voltage or something, where crystal clock is supplied, right? In a normal projects, in your case, you would be relating it with the crystal clock. So once this clock is supplied to the input, then only the actual functioning of the chip would be coming into existence. So this CTS is a domain, or you can say subdomain, where some industry standards are being prepared that for this much amount of speed, the clock frequency, this particular technology or particular component size, or you can say this distance should be kept, and how exactly like the tool will help you to guide that what components should be placed at which point, and how you can say efficiently you can place and get these things done, that is, and with the lower or the lowest power consumption. This will help you in at that point. So majorly this 7, 8, 9 points would be more of a common field, you can say, physical design. It is named as physical design. So the entire physical design team, engineering team, does this job from point number 6, like floor planning, then placement and routing. There is clock tree synthesis, and even there is point number 10, that is final verification, but it has a subdomains associated internal to this as well. But it is you can consider it as a sign off phase or the final phase, where the engineering team would give a green flag that okay, the entire ASIC flow has been well tested properly, and we are good to go for the actual chip to be getting fabricated and coming in as a hardware, instead of the you can say back end work which is done till now. The design which is prepared, the verification that is done, and then the whole design process, the placement, routing, floor planning, whatever things, this clock tree synthesis, whatever is done, now everything is correct, that is as per our application what is required, and now we can proceed to get it inside the fab foundry, you can consider, and prepare an actual hardware or the chip, and then we can use that. So this is what the point number 1 to 10 is the ASIC industry associated with, and the engineers associated across each of these subdomains. So this entire cycle, I would say that it is time consuming, and you can think of approximately minimum of 1 to 2 years for large medium scale, I would say medium scale applications, where based on the application, all these subdomains would be working for their particular functionality, and together they will bring up the entire process, and the actual chip would be manufactured. And even this point number 11, that is GDS2, where as I was mentioning that in the foundry, you can search like how exactly the foundry looks like, and how the chip is manufactured from the die size. basic die, how the different electronic are components like transistor and gates and all those stuffs are connected and formed as an hardware. So this 11th point is for that actual conversion of this raw logic into the hardware chip. So that is this GDS2, and the final part after which the hardware is in our hand and we can use that for a particular application, and inside numerous applications, not only for a particular application, you can reuse it for multiple applications as well. So for one example, let's say USBs or the Bluetooth is a common feature which we are using in our day-to-day life, right? So for even for that part, there are particular chip, you can say ASICs, that are associated for the USB. Then for the Bluetooth, there are small, very small in size nowadays. You can think of it with a naked eye, we can't even see that part, but that is so small and that are used for a particular application. So this is the beauty and the power of our engineering team and the engineers, where the idea is being converted to actual application hardware, and that is used for the particular requirement of equipment or the hardware, and which makes our life easier, as I was pointing you earlier. So yeah, this is what ASIC flow looks like. I hope it seemed to be interesting to you and you could relate it to some point. Now I would walk through brief of some domains of them, the major domains where what actually the role engineer plays in each of those domains. So here, first point, as I was mentioning, the specification. So based on the requirement gathering, there is a specific research and development R&D team for this specification, who would be gathering the information for the requirement, that what exactly the requirement is and the functionality is, and based on that functionality that is required to the customer, they think of a specification, you can say, or the requirement document, where okay, this is the requirement, and for this we want to have this ASIC being prepared. So based on the particular application, we want this IC to be designed. So this specification is the first step to the entry of this ASIC flow. In that, the features and the functionality are identified and documented in a proper manner. And then it also has a separate, you can say, designing or the planning for the chip, how exactly the chip flow would be, and the die size and all the thing, like what the actual size of the chip should be, what the power and power consumption should be. So even that type of analysis are done at very early stage and thought of at the very early stage, at the initial stage itself, you can see. So this kind of planning are very necessary, so that it is helpful at the later stage. Then third point here is architecture and microarchitecture. So this is again a very, you can say, important point in terms of planning, where based on the architecture, this will help you reduce your time, effort, as well as creating a better product in terms of power and you can say efficiency, based on the architecture being prepared. So there are many iterations and round of reviews done for this single architecture that is being finalized. So architecture team would work for multiple type of architectures, and they would decide at the end for one particular architecture based on multiple requirements and the pros and cons of each of the architectures. So yeah, this is again an important point. This all for this entire specification, as you can see, there is a domain, but it is more of an experienced domain, where after a certain stage, when we have more information on this part, we can enter into this domain and we can contribute in this part. Then the second point is the RTL coding. So as I mentioned that design team or the design engineers are associated with this RTL design engineers is a field. So in ASIC there is a field you can name it as an RTL design engineer. This is the you can say tag name associated with the engineer for the RTL designing. So this RTL design team would code the actual design in the VHDL, the Verilog hardware descriptive language, and create a synthesizable RTL code which can be used with the help of some tools to convert into like the with the entire process and the tools it can be converted into actual chip. So then for this there are many tools and many vendors of tools that are used for coding and its compiling. So here you can see one is named as graphical tools like Summit Designs or Menta Graphics are used for this RTL designing and compiling part. So the tool itself helps you providing some suggestions as well as the engineers code it in a efficient manner so that it would be efficient and you can say different from what it is currently if there is anything in market. So what new things they can be adding as a feature and requirement. So based on that they would code that in the tool itself, or sometimes it is written manually inside the files as well. So it is manually written coding as well, which would be later on converted to synthesizable code with some other tools as well. So inside this RTL coding, the thing I have put here is you can relate with your academics is there are different kind of RTL structures, the behavioral structure, the structural Verilog coding, which you might be doing is a part of your curriculum. So you can relate it like how exactly that coding is done. And again, the base for this you can consider as a C language itself, where the assembly language for the CPU and for the other part we are considering C as our base language, right? So for this hardware there are this specific language which has some addition to that C part, but the concepts are again the same. The OOPS concept you can relate here. So the base is common, but there are some additions to it which would be actually helpful in for the hardware and the hardware descriptive part, where which would be later on converted into the actual hardware and the netlist. So these are the three types of Verilog coding styles. Then test bench and simulation. So for test bench also there are specific language and tools which are used. So in our case for verification, you can say there are various vendors and we are using different vendor tools like Cadence, Verilog, Excel, Menta Graphic, Model Sim. And beyond that, there are also multiple tools in the market available which can be used for this verification. Synopsys is again one of the vendors which provide this platform for verification part. So finally, the logically correct RTL code is obtained once the test bench coding and the simulation. Here, step 3, you can see after the RTL coding is done, the engineers working on the verification team would be creating one test bench or kind of stimulus structure, which would be testing this design, RTL design, which is prepared by another engineering team. And once that simulation is done and results are passing and as per the expectation, then the next step is coming into picture. And if not, then again it needs to be looked upon that what are the issues and what are the bugs that are not causing it to pass and not allowing it to work as per the expectation. So the cycle would be again repeated until the point it is not actually working as per the expectation and the test case is not passing for the particular feature. So this is what test bench and simulation looks like. The synthesis, as I mentioned, was the industrial standard where the RTL code is converted into optimized logic and gate level representation. And this can be directly, once the synthesis is done and the synthesizable code is in our hand, we can use that directly for the foundry process, where then the synthesized netlist is used for creating a hardware. So there are tools and technologies which are used for first of all converting the RTL logic into this synthesizable netlist and code, and then later on the synthesized netlist to be converted into actual hardware. So, and there are, as I mentioned, the tools has some industry defined or the specified standards and libraries inbuilt inside it, which can be used for converting. Like there are different, as you are saying that there are different vendors inside the market, across the market, and we can relate like at the end it is all particular standard which is to be followed, and in the foundry that is the common format which will be used for converting that synthesized code into the actual hardware. So this is where this synthesize or RTL synthesis domain comes into picture. Then automatic place and route is again with the help of tool. There are daily there are upgrades and you can say automation done for this particular domain as well, where the tools are made so smart that it will route and place the our transistors and gates in a particular manner, so that it is very efficient and very you can say fast when the actual hardware is being coming into picture. So in this particular part we are seeing that there are many intelligent or smart tools coming into market, which is helping our engineers to make it more the life of an engineer more easy, and even the actual hardware to be more efficient. Then the logic verification. So this is kind of end structure where actual entire process you can see here, from specification to actual working netlist or the synthesizable netlist. So now let's say we had that specification in our hand and we have prepared some design, and we are confirming it as a thing which can be sent to the foundry and the for actual hardware preparation. But who will make sure, or how we can claim that it is this is what we that was the requirement and that is what it is sufficing? Because at times it might be the case that the interpretation of the things which are that was bring up at the time of specification and what is actually implemented, so that they both might be differing in their terms. So this is a important point where we do a check that actually what the requirement was and what actually the implementation what it is done, so they are in sync and they are as per the expectation. So in this case the entire flow is looked upon, we can say, and if there are any failures or fix, we can again go back to initial step, that is step 2, and if not, then we can move to end this stage where we can move ahead with the actual manufacturing of the chip. So that is kind of, again, in this there are sub technologies which are used, LES, LVC, which will help us to do this logic verification. And the last step is the tap out, where the design, once this design is finalized and freezed, and we are saying that it is a bug free and working properly, so it will it is sent to the foundry and actual chip is being created. So that is where this magic piece comes into our hand, and it does the wonders for the different electronic gadgets, where it makes our life easier, as I pointed at the initial point. And at that point you will be the happiest person when you will take that piece of hardware into your hand and look that oh, you worked on this amazing technology, and it is serving to lakhs and millions of people across us, and even in our day-to-day life, the gadgets which we are using, you can relate yourself with that part, that okay, I worked on this particular technology and this particular design. So that is something which will give you the satisfaction and the proud that the field you have studied and the curriculum which you have done, the studies which you have done till now, you have worked actually in the industry for that part, and it is now kind of small, that and tiny chip that is working for this many applications and this many features. So that is what I would say this ASIC field is all about. And there are many companies and industries in our across our world, where these different companies are working for different kind of applications and different kind of chip manufacturing. So it is a great scope to explore, and very, I would say, rich and interesting field in terms of relating your actual curriculum and the knowledge to what is there in the hardware. Like, this is the first thing. Once the hardware is there, then there is the UI and the different application based of fields, embedded field which is there. It is again a separate field to explore and learn. So based on your knowledge, as I mentioned, you can select a field, but the ASIC is the first step, you can say, where actual before the chip is being manufactured, this all flow and the process is being followed, and then the actual chip is manufactured, and you can use it with different kind of UIs and applications at the later stage. So yeah, that is what I had about the ASIC industry and ASIC field. So, and I would definitely, like, I am definitely proud of this field, and I'm working with this since more than 5.5 years. So yeah, I would thank you all for listening to me, and I hope I could help you gain some knowledge in this field and understand things a bit more better way than what you are learning in your current academics, so that you can try to think of yourself, analyze yourself, and go ahead with your field and choose the field of your interest. So yeah, thank you. That's it.
Thank you, Pranav. Thank you, Pranav, very much for spending your valuable time and knowledge for the students of our Parul University and Parul Institute of Engineering and Technology, and especially especially for the students of electronics and communication. And Pranav, the way in which you present, okay, was very nice, and the ASIC design flow, total 11 steps that you explained, okay, was really wonderful. And even you are might be knowing that in our semester 6 in VLSI, okay, we have studied in a chapter number 1 about ASIC design flow. But and you know, I have been teaching that subject since many years. Okay, but in from your today's presentation, even I got to know many things in the with industry perspective. So once again, very much okay. Thank you very much for spending your knowledge and time. Okay. And Pranav, here I have a couple of questions from the students. Okay.
Sure.
I have just sent you the messages in your chat box. The message from the fourth sem student, Utsav Marodia, is there. And he has asked the question with reference to the ASIC design flow slide. Okay, so in that you explained about total 11 parts. So he has a doubt in step number 5 or 6, and he has asked the DFT department checks the hardware and perform tests as to rectify impurities in the hardware. So can you explain what kind of impurities, and it is a code bug or hardware transistor gate misplacement? So this is the question he has asked, Pranav.
Yeah. Okay, so sorry, I didn't recall his name, particular student, but yeah, to answer to his question.
Utsav is there.
Yeah. Hi, Utsav. So yeah, it is a good question, and basically the DFT part which you asked, like where exactly they work in. So during manufacturing time, it might be the case that sometimes the wiring may be this is a very, you can say, a common issue which I am explaining. It might be not the case, like at that level there would be many precautions and checks that would be there in their flow. But for a small example to give you, let's say we are connecting two wires and we are expecting some output to be passed through that connectivity part. So it is not connected properly, or it is short or something like that. This kind of different issues, or the gate itself is faulty. The gate logic which we are using, this is not a common issue, you can say, but there might be very 1 in a million case kind of thing where these kind of issues might occur. So in this such cases where this connection issues or the connectivity are not done properly, so in that case the data would not flow to the endpoint with the correct value which we are expecting. So after the manufacturing is done, if we want to test like if it is not working correctly, and if we want to validate inside that exactly at which breakpoint the issue is being caused, and if we want to identify that point, at that point this test vectors and the skein chains and different things which they have inserted as a part of logic inside the design, that would help you to break up things, divide the entire issue, and get you that okay, till this point the data is reaching correctly, and after this point I'm facing issues. So the issue is somewhere between. You can minimize the area where the actual issue is, and you can that way get to closer to the issue and reach where exactly you can pinpoint where exactly the issue is. So yeah, that is where this DFT guys have their role to play, that they are deciding on which are the critical points inside this entire design and where to insert what kind of test vectors. So that can help later on after the manufacturing is done.
Okay. Pranav, we have another question, and the question that is actually coming from 2018 pass out students. So right now we can also call him as an alumni. Mr. Harsh Parmar is there, and he is on the Facebook Live, and he has asked the question that which is better between ARM Cortex or VLSI hardware. This is the question from Harsh Parmar.
Sorry, if I understood the question correctly, so he is asking that what is better between ARM Cortex and
VLSI hardware. Yes, the question he asked me on WhatsApp.
I didn't follow him correctly. Like ARM Cortex is a processor, right? Like what processor you are selecting in, and VLSI hardware is the domain, like actual domain. VLSI is the entire, you can say, superset of this processor which you are using inside this VLSI. So choosing between different processor is a point on for which you first of all need to decide on the requirement, like what kind of requirement you have, and based on your requirement you need to choose the processor wisely, like what kind of application you want to do, what is the speed, what is the end goal or end result you are expecting from that. Like you want sensors associated with it, what is the, as I mentioned, what is the application with that. So processor is the small part, or you can say subset of this SoC of the VLSI, which is actually VLSI is the ASIC. So VLSI is the subject, but ASIC is the chip. So in the SoC entire chip, this processor is a small part of it, and you have to choose it based on your requirement.
Thank you, Pranav. Another questions are coming up, so I'm going to short it up.
Yeah.
Another question from the 4th sem student, Suman is there. Actually, he has just completed the diploma and he has joined the degree program. So he is asking that what subject to focus on during 3rd and 4th year for this field. So he is interested to make his career in this VLSI domain. So he's asking the question, the subject that he would focus during 3rd and 4th year in order to make his career in this field.
Sure. Yeah, that's good. He seemed to be interested in this. So yeah, the subjects, as Umang sir also rightly pointed, like VLSI itself, the first chapter itself has this ASIC flow. So from that you can consider it like VLSI is the base of this, where you can learn the processors, controllers, all these different technologies inside VLSI. It covers a wide range of part, but yeah, it is altogether termed as VLSI. But then inside it, there are you can dig deep into subfields, and even from other subject perspective, you can relate it with antenna. Will help you digital DLD, digital logic design. So this kind of subjects would help you in the gate. Understanding how the gate works, how the transistor work, NMOS, PMOS, CMOS. So these all subjects would have those information where what electronic this equipments and the devices are doing. So those would be helpful to you. You can focus on that.
Okay, Pranav, and one request on behalf of all the students from my side. In future, if we need any kind of help, then I am expecting help from your side, and it would be appreciable from your side if you are going to share any kind of material, okay, with the students, so that they can prepare it and they can crack the interviews, they can appear for they can make the career in the field of VLSI. So it's a small
Sure,
request
sure.
on behalf of my all the EC students. Okay, Pranav.
Sure, sure, definitely, sir.
Okay, so once again, Pranav, I would like to thank from bottom of my heart, okay, by for spending your valuable time and share your knowledge. Okay, so once again, I thank you, and by this, I conclude this session, Pranav.
Okay, thank you, everyone. Bye.
Thank,
All the
thank you,
best for your careers.
thank you, Pranav. Thank you very much. Thank you very much.